Hi, I am JunYoung Choi, a postdoctoral researcher at Korea University. The research I will present today is MitoVis, a unified visual analytics system that enables effective analysis of neuronal mitochondria. By previous various studies, it is known that the morphology of mitochondria appears differently depending on the structure of neurons such as dendrites and axons, or the presence of neurodegenerative diseases like Parkinson's disease. These morphological characteristics of mitochondria can be used as a biomarker of cancer phenotype and drug response. The analysis of mitochondrial morphology is usually carried out through repetitive experiments on numerous data. And to perform such analysis, preliminary tasks such as the neuronal structure segmentation, mitochondria detection, and generating morphological features are required. However, since most of these preliminary tasks are done manually, it takes a lot of time and effort. Recently, a few studies have attempted to automate these tasks through deep learning, but it is not easy for most analysts, who are not computer science majors, to properly utilize these technologies. In other words, while many techniques have been developing for the analysis of mitochondria, most analysts are still conducting analyses using inefficient ways. To solve this problem, we collaborated with neuroscientists to set the main tasks and design goals necessary for designing an analysis system. The essential tasks include neuronal structure segmentation, mitochondria detection, and morphology analysis. The design goals are that even users who are not familiar with deep learning should be able to use the deep learning method easily, be able to obtain results of a quality sufficient to perform analysis by quickly and easily correcting errors existing in the deep learning results, and should be able to effectively perform morphological analysis on numerous data. Based on this design rationale, we have developed MitoVis, a unified visual analytics system for end-to-end neuronal mitochondria analysis. MitoVis takes as inputs the venous confocal microscope images containing the neuronal structure signal and the MitoM scarlet confocal microscope images containing the mitochondria signal. For these inputs, pre-trained models perform neuron structure segmentation and mitochondria detection to create initial results. The user can correct errors in these results and use the correction information to retrain the deep learning model, enabling interactive deep learning to gradually obtain more accurate results. Through the generated neuronal structure and mitochondrial information, users can perform various analyses based on image and morphological features. I will explain each part in more detail. For neuron structure segmentation, first, a U-net-based deep learning model generates initial segmentation results from the venous images and separates them into neurite units through neuron tracing. To more easily correct errors present in the initial deep learning results, MitoVis introduces a novel active learning framework based on recent contrastive learning, which allows for accurate fine-tuning of the neural network model. The workflow is as follows. Perform initial pixel-level neuron structure segmentation on the input confocal microscopy images using a pre-trained deep neural network model. Decompose a neuron into neurites using a neuron tracing method and generate image patches over the neurites. Assign patch-wise labels from the initial structure segmentation result. Train the patch-level classification model with contrastive loss. Deploy the trained classifier to the data. Update per neurites labels, and correct label errors using visual guides. When the user selecting one erroneous neurite and correcting its label, similar neurites with errors are recommended and displayed as insets around the user-corrected neurite. The user can either perform corrections directly on them or change the current image view to the location of the recommended inset. Fine-tune the patch classifier using the initial and fixed labels. Repeat these until an acceptable result is obtained. For mitochondria detection, a U-net-based deep learning model generates initial segmentation results from the MitoM scarlet images, and the segmentation labels are divided into individual mitochondria objects using the connected component method. To easily correct the errors occurring here, 4 interactions are designed: excluding, splitting, merging, and including. The user can select overlapped objects or noise objects and correct them as the background by the excluding interaction. The splitting interaction divides one object into 2 objects based on the line drawn by the user. Contrary to the excluding interaction, the merging and including interactions create a propagated region by resulting in a connected component from the user's drawing input. With the structure label and mitochondria objects created in the previous steps, morphological features are generated for each mitochondria object. Based on these features, various analytical tasks can be performed. In parallel coordinate plots and 2D projection plots, users can create data subsets belonging to the desired feature range, and can record and conduct comparative analyses of the statistical values of these subsets. To validate the performance of our proposed visualization-guided error correction method, we conducted a user study with 5 domain experts. Each participant performed tasks to correct errors in the neuron structure segmentation results using 3 methods. First, manual pixel level correction. Second, neurite level correction. And third, visualization-guided neurite level correction. As a result, compared to corrections made at the manual pixel level, the methods corrected at the neurite level showed faster and more accurate performance. It was also confirmed that using visualization-guided methods reached higher accuracy more quickly compared to when it was not used. Furthermore, we conducted analyses on actual analysis cases through MitoVis in collaboration with 2 neuroscientists, validating the usability and efficacy of MitoVis. As a result, MitoVis achieved a speed-up of more than 6 times compared to traditional analysis methods. Additionally, the neuroscientists mentioned that MitoVis is capable of quickly analyzing images for various subsets and groups, which is useful for multiple data screening tasks. MitoVis is an all-in-one visual analytics system designed to perform neuronal mitochondria morphology analysis quickly and effectively. Through the active learning framework and visualization guide, we have enabled fast and accurate analyses. It allows for flexible analyses by enabling the generation of various mitochondrial subsets using feature-based and image-based subset generation methods. We plan to apply MitoVis for in-depth analysis of disease models and neuronal cell types in the future. This is end of presentation. Thank you for listening.